to specify, in this case, I actually have to specify what the domain is for my inverse function. All right, not too bad. Let's try another one. Let's take a look at g of x equals 1 over x plus 1. We saw the graph of this function earlier. Remember, we saw the graph of this function earlier. This function does have an inverse. What is that inverse? How can I find it? This one over here, this one was a little easier, a little more intuitive as to where the inverse came from. This one maybe a little bit more challenging to identify how to find the inverse. Now, there are procedures that one can go through to craft the inverse function. And typically, what you'll see is you'll start with, well, first of all, write everything in terms of x's and y's. What's usually the next step? You switch the roles of the x and the y. Okay? So this would then become x equal 1 over y plus 1. Right? And now what you do is you take this expression and you solve it for y. So now I'm going to solve for y. Get our g inverse. Okay? Alright, so how am I going to solve this for y? What do I do? Multiply y. Okay, we're going to go ahead and we're going to multiply the denominator across. And so we're going to get x times y plus 1 equals 1. Then what? A couple of different options we can do here. A couple of different things we can do. One thing we can do is we can multiply the x through everything. It's perfectly legal. It's a fine operation to do. So we can make it xy plus x equals 1. Okay, and then what do we do from there? Well, I'm trying to solve for y, so I would move the other x over and get xy equals 1 minus x. And then obviously the next step would be divided by x, so y equals 1 minus x over x. That's one way of doing it. We could have gotten to a similar answer by just, at this step, dividing by x. Right? Divide both sides here by x, we get y plus 1 equals 1 over x. And then I just subtract the 1 over. 1 over x minus 1. Okay. Both of these are the inverse. Both of these. These are the same answer. They're just written in differently. Whichever one you're more comfortable working with, go for it. But these are the inverses that we get for this function. All right, so we found our inverse function. Now we want to find the domain and range of the inverse function. Okay? Well, maybe we can start by identifying the domain and range of our original. What is the domain of our g of x? What values can I plug in to the g of x function? Okay. Notice the rule that I have to obey, the rule I have to be careful of here, is I can't divide by 0. So the only way I can get 0 in the denominator would be if x equals minus 1. So my domain here would be everything except negative 1. So there's my notation for that. Because of my vast knowledge of inverses, I know that that's also the range of f of g inverse. Right? That's what we said earlier. The domain of the original is equal to the range of the inverse. All right? What about then range of g of x. And if you want, we can sort of look at the picture of the g of x function. Graph it down here again, just to so we have it. Okay. This is what the graph of y equals g of x is. That's the graph of our original function. What output values am I getting from this graph? Another question, what output values do I not get? 0. Okay. The only thing that I don't get from this graph is the value 0. Value 0 is the only thing I can't get out of this graph. And if you look at the equation over there, you may be able to sort of justify that to yourself. You can get everything else, but 0 you can't get because when we have a fraction like this, the only way that fraction is ever going to be 0 is to be at the top is 0, top's never 0. So that's the only number we don't get out. All right, so our range here is everything but 0. And that then is our domain for the inverse function. Okay? All right, very good. We can graph the inverse now if we want. In graphing the inverse, I personally would probably go with this second function. I'd probably go with this notation because I can identify this graph as being the graph of 1 over x shifted down 1 unit, right? If I go through and look at it that way, I should be able to identify what that graph looks like. 1 over x shifted down 1 unit should be something like this. There. This is the y of g inverse of x. Okay? That's what that graph looks like. I got a couple minutes left. And in my remaining time, I'm going to take a look at this graph for just a moment. I think that's double check.
What was that thing that you would put a star by earlier?
Oh, the linear function one? Right. Linear functions, as long as they're not constant, as long as it's not a constant function, which in a sense is not linear, but in a sense is because it has a graph of the line. Linear functions that are not constant are invertible. A constant function is not invertible because it fails miserably at the horizontal line test. Because I can draw the same line up there and it crosses itself an infinite number of times, which is an epic fail in terms of being invertible. Okay? So, thanks for reminding me about that. I didn't forget. Let's see. The last thing I want to talk about is just relating the inverse function, the graph of the inverse function to the original function. And I deleted the best example that I had before here. Sorry, let me just write this up here one more time real quick. The graph of square root of x, the graph of x squared for x greater than 0. One of the properties of inverses that is very nice is that graphs, if you're using graphs to identify whether a function has an inverse or not, it's sometimes difficult using that picture to identify what the inverse function graph is going to look like. But there's a nice property that all inverse functions have to obey that allows you to graph that if you can visualize things in the right way. One thing you'll notice, this is the line y equals x that I'm dotting in here. a function and its inverse have a nice property in relationship to this line y equals x. And if you look at the graph I have on the board and you look at the way this dotted line sort of runs through it, hopefully you can see that the graph of a function and its inverse are mirror reflections if you reflect them along this line. Okay? That's one way you can graph the inverse function if you don't have a formula for it. Is you can graph the original function, draw on the line y equals x, and then just fold the paper over and sort of sketch in where the original function was in that little fold over. Okay? So f of x and f inverse of x are mirror reflections across the line y equals x. You can check it with the other functions that we have on the board here. You'll see that, yep, it sure enough works. And so I'm not just blowing smoke, this is really actual math. Okay? This is real. Next time, we will look at some of the algebraic properties of functions and their inverses. But that's all for today. Have a good day. Make sure you take the quiz by 5 o'clock if you haven't done so already.